Hello everyone, myself Dr. Sadanand Kumar, Assistant Professor, Department of Physics, AJ Institute of Engineering and Technology, Mangalore. And today I am going to discuss about Eigan function and Eigan values, time-independent Schrodinger wave equation, application of Schrodinger wave equation, that is particle in a box, and some applications related to it. In the last class I have discussed about the properties of the wave function. Wave function should be continuous everywhere, wave function finite everywhere, and wave function and its first derivatives are continuous everywhere with respect to their variables. And today I'll start with the Eigan function. Now, what are Eigan functions? The Eigan functions are those wave functions of quantum mechanics which possesses the properties that they are single valued, finite everywhere, and also their first derivatives with respect to their variables are continuous everywhere, which means the three properties of wave functions are satisfied for a wave function. Such wave functions are called as Eigan functions. In order to extract the information from the wave function, quantum mechanics gives rules to predict the results of measurements. The rule consists of some mathematical operations. So, to do some specific operations on wave function, operators are required. So, let us see what are operators. That means to do some specific operations on a wave function, some sort of operators are required. To understand this, let me take an example, square root of 3, where square root is an operator and taking the square root of 3 is an operation. Similarly, integration of x square dx, that integration is the operator, and integrating with respect to x is an operation. See, likewise, in quantum mechanics, each type of measurements, there is a kind of operator. We have momentum operator, likewise we have energy operators. In quantum mechanics, we can write this momentum operator as h by 2 pi I into dou by dou t. Similarly, energy operator as minus h square 8 pi square m into dou square by dou t square. So, once if you have a Eigan function and operators, it is possible to evaluate the Eigan values. So, if the Eigan functions are known, quantum mechanical operations can be used to evaluate the physical observables. See, energy is an physical observable. If you do the operation on this energy parameter, in which each Eigan function gives rise to one energy value. Also, there are restricted set of Eigan functions. Correspondingly, there are number of Eigan functions, in fact Eigan values. All these wave functions may not give proper results or values of physical quantity when operated by an operator, because postulates of the quantum mechanics says that only possible values can be allowed for a physical quantity like energy, angular momentum and momentum, etc. When an operator is operating on Eigan function, it produces back the wave function and multiplied by a constant. The constant values obtained for a physical observable are called Eigan functions. Mathematically, I can write a cap psi is equal to lambda psi, where a cap is the operator and psi is the wave function. By back, it produces a constant lambda and Eigan function, where lambda is happen to be a Eigan value of that particular physical observable. Example you can see here, differentiation of e power ax, that is a into e power ax, where differentiation is the operator operating on the function. By back it will give rise to constant, a is a constant, and it will produce us back the same function e power ax. That is how it is. If the energy operator is operating on the Eigan function, then the values are called energy Eigan function. Likewise, if the momentum operator is operating on the Eigan function, then values are called momentum Eigan values. So, the values of the physical observable such as energy or momentum for which Schrodinger wave equation can be solved are called Eigan values. As we know that the wave function in quantum mechanics accounts for the wave-like properties of a particle, and the wave functions are used to solve the fundamental equation called Schrodinger wave equation. Schrodinger wave equation can be set in two different contexts. One which is general and takes care of both the position and time variations of the wave function. They are called time dependent Schrodinger wave equations. It includes the imaginary quantity and is complicated. The other one is applicable only to steady state conditions where wave function can have variation only with the position but not with the time. It is called time independent Schrodinger wave equation. It is simpler than the time dependent Schrodinger wave equation. Okay, now let us derive the Schrodinger's time independent wave equation. For this, let me consider a particle of mass m moving freely in the positive x direction in a stationary potential field. The wavelength of the associated de Broglie wave, that is lambda is equal to h by p, because we know that particle can behave as a wave nature. So associated wavelength has been given as h by p. And wave function of the de Broglie wave associated with a particle psi is equal to a into e power I open bracket kx minus omega t, where a is constant, k is the wave vector and omega is the angular frequency. Particle is moving in a steady or the stationary potential field, then the potential energy of the particle does not depend on time but vary only with respect to the position of the particle. Now differentiate this expression psi is equal to a into e power I open bracket kx minus omega t with respect to x twice. Therefore, you can see here the first derivative with respect to x, therefore ik, and double derivative, it is I square k square. In this expression I square is minus 1, therefore the expression will be reduced to minus k square psi, where psi is again the part a into e power I open bracket kx minus omega t. But wave vector k can be written as 2 pi by lambda. Substituting this expression in the expression number 2, d square psi by dx square equal to minus 4 pi square psi by lambda square. Now you can write this expression in terms of 1 by lambda square, that is equal to minus 1 by 4 pi square lambda, means 1 by 4 pi square psi into d square psi by dx square. If m is the mass of the particle moving with a velocity v, then it possesses the kinetic energy. That kinetic energy is given as half mv square. By doing some rearrangement, in the sense multiplying and dividing by m to this expression, you will get p square by 2m, where p is mv. But according to the de Broglie hypothesis, lambda is equal to h by p. From that you can write p is equal to h by lambda. You can substitute the value of p in the kinetic energy expression. So that kinetic energy as h square by lambda square into 2m. That's equal to h square by 2m into 1 by lambda square. Some rearrangements where we have a 1 by lambda square. Now you substitute the 1 by lambda square term. We have a expression here. This you can substitute here. If you substitute that, you will get kinetic energy term as minus h square by 8 pi square m psi into d square psi by dx square. So after evaluating the kinetic energy term, let us see if V is the potential energy of the particle, which depends on the position of the particle in the field, then the total energy of the particle is kinetic energy plus potential energy is equal to total energy. Therefore, kinetic energy term we have already solved. Add potential energy term, so that you will get d square psi by dx square equal to minus 8 pi square m by h square into E minus V into psi. So by taking the left side term to the right side, the equation can be written, and that equation is happen to be Schrodinger's time independent wave equation. In 3 dimension, you can write this expression as d square psi by dx square plus d square psi by dy square plus d square psi by dz square plus 8 pi square m by h square into E minus V into psi is equal to 0. Next concept, the application of Schrodinger wave equation. By considering the Schrodinger wave equation, we evaluate the Eigan function and the Eigan energy value of a particle in a one-dimensional potential well. Suppose a particle of mass m, which is free to move in a x direction only in the region from x equal to 0 to a, that you can see in the slide. In this region, potential energy is 0, which means V is equal to 0. Out of this region, it is taken to be infinite, which means that particle is bound within the limits. That means x equal to 0 to x equal to a. Such a configuration of potential in space is called as infinite potential well. A particle bound within such a infinite potential well is defined in 3 dimension is particle in a box. Now we have a Schrodinger wave equation. Let us implement the Schrodinger wave equation in 2 conditions, within the well and outside the well. That means on the width the x equal to 0 to x equal to L, the other condition is outside the well. So let me take up the first part, outside the well, where the potential is infinite. That means V is equal to infinity. Just substitute V term in the Schrodinger wave equation. So equation becomes d square psi by dx square plus 8 pi square m by h square into E minus infinity into psi is equal to 0. So solution for this equation is psi is equal to 0 in the sense there is only possibility that particle is present outside the well. Psi is 0 in the sense modulus of psi square is also 0. That means the probability of finding the particle is outside the well is 0. That is the meaning. That means probability of finding the particle outside the well is 0. We are highly certain that the particle is restricted within a width of the well, that is x equal to 0 to x equal to L. Okay, let us go to the next condition, that is implement the Schrodinger wave equation in the width of x equal to 0 to x equal to L. Here the potential is 0, therefore equation will becomes d square psi by dx square plus 8 pi square m by h square into E psi is equal to 0. Now the constant term, that is 8 pi square m by h square into E, that term is treated as some constant k square. Therefore equation reduces to d square psi by dx square plus k square psi is equal to 0. I will call this equation as equation number 3. This is a second order differential equation and it has got many solutions, but all these solutions are not a correct one. Now let us write the solution for this, that is psi is equal to a sin kx plus b cos kx. By applying the conditions 1, that is at x equal to 0, that means on the wall one side, x equal to 0, psi is equal to 0, that means wave function is not existing, mean particle is not existing. Then equation 4 becomes 0 equal to a sin 0 plus b sin 0, which means b is equal to 0. The second condition is at x equal to L. You can see the well picture, potential well picture, x equal to L, where psi is also 0. You just substitute these two values in the equation number 4. Equation 4 becomes 0 equal to a sin kl plus b cos kl. So since b is equal to 0, a sin kl is equal to 0. That is the expression what we got after implementing the condition 2. Now sin kl is 0 or a is equal to 0. A need not be 0 because it is a constant. Therefore, we need to take sin kl equal to 0. In order to make sin kl is equal to 0, kl can take the values of integral multiple of pi, which means kl is equal to n pi or k equal to n pi by l. Now the equation 4 becomes psi n is equal to a into sine of n pi by l into x. N pi by L into x, that is a permitted solution. Okay, after getting the permitted solution of a wave function, we have a concept of normalization. Let us implement the normalization concept, because we are highly certain that a particle is bound within the width of the well between x equal to 0 to x equal to a. Therefore, I can write the chance of finding the particle in the well is 100%. So integration between 0 to L, probability density is equal to 1. That means integration between 0 to L, the modulus of psi square dx is equal to 1. So this concept is known, it's a normalization concept. And just substitute the wave function here and evaluate. So here a square sin square n pi by L into x dx is equal to 1 we will get, but sin square theta can be written as half into 1 minus cos 2 theta. Just you substitute that expression in the equation. So integrate it so that second term in the expression, here it is second term, will become 0 because it is a multiples of pi you will get, sin pi. Sin pi multiples of n pi you will get sin term, therefore it will become 0. Only the first term retains, therefore a square by 2 into L, that's by applying the limits we will get that. So a equal to square root of 2 by L. Just substitute the constant value in the wave function, so that will be the normalized wave function of a particle in a one-dimensional potential well. The same expression represents the Eigan function of a particle inside the potential well. For each Eigan function associated an Eigan value, that means the allowed energy states with that particle. Now we have treated that k square is equal to 8 pi square m by h square into E. Also from the concept that to make sin kl is equal to 0, the kl can take the value of n pi. From that you can write k square is equal to n pi by L whole square. So equate these two. From that you can get the term for energy, En is equal to n square h square by 8mL square. Since n is restricted, particle energy is restricted to a certain values. Where n is a quantum number, the energy values En are called Eigen values. Lowest energy of the particle is called 0 point energy or ground state energy and is given by E1 equal to h square by 8mL square. Here you cannot take n equal to 0. Why? Because if you take n is equal to 0, that is contradiction to our statement, in the sense that we are highly certain that a particle is present within the well width of x equal to 0 to L. So it is if you take psi is equal to 0, the particle is not existing. That is the meaning, that is the reason why we are not taking n is equal to 0. So we have to take the ground state energy n is equal to 1. So first excited state energy E2, that is n square into E1, that will be the total energy, that can be written as 4 into h square divided by 8mL square. Similarly for second excited state, n equal to 3, E3 equal to 9h square 8mL square. Let us evaluate the wave functions, probability density and energy levels for the particle in a infinite potential well. Already I have discussed about the energy levels of the ground state, first excited state and second excited state. Let us see the acceptable wave functions and the probability densities. Now consider the acceptable wave function when a particle in a one-dimensional potential well, psi n is equal to square root of 2 by L into sine of n pi by L into x. So in the ground state n equal to 1, therefore psi 1 equal to square root of 2 by L sine of pi by L into x, where I have substituted n equal to 1 in the expression. Now we give different values of x in the expression. So x can take the values 0, L and L by 2 because the particle is in the ground state. So if you give different values, the psi 1 will become 0 at x equal to 0 as well as x equal to L, and also psi 1 becomes maximum when x equal to L by 2. If you put in place of x here, it is L by 2 L, L cancels out, so sine pi by 2, that's why it is maximum 1. So if you plot the graph of psi 1 versus x, so you can see the nature of the graph. So central region it is maximum, and the probability density, in order to conclude that the probable position of the particle in a potential well, we have to draw a plot of probability density versus the x, that is modulus of psi square versus x. So nature of the graph can be seen, and you can conclude that when the particle is in the ground state, particle cannot be found at the walls of the box, and the probability of finding it is maximum at the central region. So that is the case of ground state. Let us take first excited state, where n equal to 2. The Eigan function for this state is psi 2 is equal to, just substitute n equal to 2 in that expression. So you can see the expression there. And now again, since the particle is in the first excited state, you can give the different interval that psi is equal to 0 and maximum at a different value. You have to evaluate by substituting x equal to 0, L by 4, L by 2, 3 L by 4 and L. These are the different set of intervals you are supposed to substitute in place of x, so that you can find out maximum and minimum value of psi 2. So it is found that psi 2 equal to 0 for the different x values, that is x is 0, L by 2 and L, and it is maximum for x equal to L by 4 and 3 L by 4. And once if you get this data, so you can plot the graph of psi 2 by x. You can see the nature of the graph. The one maximum value is in the positive x direction, another maximum in the negative x directions. So what you can do is you can take the probability density curve so that it will become positive. So in the second graph, that is probability density versus x, both positive values or the peaks which are in the positive x directions. So from this graph you can conclude that when the particle is in the first excited state, particle cannot be observed either at the walls or at the center. So probable position is somewhere different than the particle which is at the ground state. Similarly, you can try for when the particle is in the second excited state by allotting different values of x. That means in the first excited state we allotted x equal to 3 different values, and similarly in the second example where we have allotted 5 different sets, and similarly third one you can go for 7 different values of x. So you can find out what is the probable position of the particle in the potential well. Let us see one or two problems from the topic. An electron is bound in one-dimensional potential well of width 1 Armstrong of infinite wall height. Find its energy values in the ground state and also in the first two excited state. It is a simple problem where given data is the width of the well, that is 10 power minus 10 meters. Also the energy of the electron in one-dimensional potential well is En equal to n square h square divided by 8 ml square. So that is the solution for the problem. Just you can substitute n is equal to 1 because it is a ground state. So you will get energy as 6.03 into 10 power minus 18 joules, and convert joule into electron volt, it will be 37.6 into 37.6 electron volts. And known parameter h is Planck's constant there, and m is the mass of the electron, and L is the width, already it's given. And for the first excited state, n is equal to 2. So energy of the electron in the first excited state, E2 equal to n square into E1. And the second excited state, similarly, n equal to 3, that is E3 equal to n square into E1. So first excited state, the energy will be 150.5 electron volt, and second excited state, it will be 338.7 electron volt. And second problem, a quantum particle confined to one dimensional box of width A is in its first excited state. What is the probability of finding the particle over an interval of a by 2 marked symmetrically at the center of the box? Now in this problem, the particle state is given. The particle is existing in the first excited state, which means n is equal to 2, and also the interval is given as marked symmetrically at the center of the box, which means a by 2. So let me draw one potential well. So 0 and a in between, the symmetrically marked at the center. Now since the particle is in the first excited state, you can put the limits between a by 4 and 3a by 4. So which means you are supposed to determine the probable position of the particle between the limits 3a by 4 and a by 4. The equation for the probability density from the Max Born approximation, that is P is equal to integration of psi square dx, and psi 2 we have the expression from the acceptable wave function when the particle is in a one dimensional potential well, that is square root of 2 by L into sine of 2 pi by L into x. Just substitute that psi n in the probability density expression and integrate between the limits 3a by 4 and a by 4. And this sine square, here also this sine square term comes. That sine square term can be written as 1 minus cos 2 theta into half. That means half into 1 minus cos 2 theta can be written. Same concept will be implemented here, and you can integrate. So once if you integrate, you will get the 0.5. So 1 minus, that is dx, actually integrate dx, that will be x, limits between 3a by 4 to a by 4. And similarly here integration between 3a by 4 by a by 4 cos of 4 pi by a into x dx. So that will be sine term. When sine term comes, it's a multiple of pi you will get. Therefore sine pi is 0 or sine 2 pi, whatever it is. If you implement the limits, that will be 0. So second term here it will be 0, but the first term that will gives rise to a by 2. Therefore it will be 0.5. The probability of finding the particle somewhere in the given interval is 50%. I will stop here. Thank you.